Want to nail engineering manager interviews at Mang and other top-tier companies? You can with USA's #1 tech interview prep platform. We have 300 plus SMEs and instructors from top-tier tech companies to help you land your dream job. We've helped thousands of engineers make their way into Mang. You could be next. To learn more, register for our free webinar.
Hi. Awesome. Cool. Let's get started. So this is going to be a system design interview. Let's see. Okay, I see that you have a whiteboard that you're sharing. Do you have a doc or something that we can use to share text? Because
yeah, sure.
I'll need,
Create one.
All right. Okay. So here's the question I have for you, and I'll explain the question as well. Let me know if you've heard the question before.
Okay.
You may have, but I mean, let me know if you know. I mean, if you already know it off the top of your head, then there's no point to it. So I want you to design a system to handle places nearby queries, right? So what that means is, given a location expressed as a lat long radius, your system should return all the places from the lat long that lie within the radius.
Okay. Design a system to handle places nearby queries. Given a location expressed as lat long radius, system will. Okay. Right. So I suppose some initial questions are. Like how often will these places, like are the places going to be dynamically updated? Like how many updates are we talking about? Like how many reads and how many updates, I suppose?
It's a super read heavy system. So you're gonna have maybe 1 million reads per second for the system, and the write queries are much lower, probably 1,000 per second or something.
Okay.
Yeah.
And how many locations? Like how many locations? How many places are we talking about?
We're talking about, let's say, an upper bound of, let's say, like 5 billion locations.
Okay, 5 billion locations. All right. And are these, like, what's the distribution of these places? Are they distributed all over the world, or?
These places are distributed all over the world.
Okay. And so when a user queries, is he querying for places nearby himself, or he can query anywhere?
Excellent question. So a user can, typically, you can query any place in the world. And this system will probably support multiple like front ends, right? So maybe some front ends like Yelp, where typically it's places around you. And for some front ends, it could be like TripAdvisor, where you're looking for stuff away from you. So the system can't make that distinction.
Okay, so users can query anywhere in the world. Okay.
Yeah.
All right, I think we have reads 1 million a second, writes 5 billion locations. Okay, all right. So the first thing I want to do is let me just think. Okay, let's just maybe start out rough. Let me delete this out. So we'll need a system that's, of course, going to let's call it a location input service. So this is going to bring in these locations into our system, and and then of course we're going to have a query service. Okay. So of course the locations that we are the system is going to handle need to be stored somewhere. So we're going to have a storage. Okay. And for now, so we mentioned that we have about 1,000 writes per second. Okay. All right. Actually, I have another question. So, like, what's the latency requirement in terms of when the writes need to be visible? Like, if I enter a new place or if I make an update to a place,
so yeah, so eventual consistency is okay. Like it can take a few seconds to show up or something. That's okay.
Okay. All right.
Yeah, it wouldn't be reasonable to expect strong consistency for updates. Yeah.
Okay.
Yeah.
Okay. So we have storage, and going back here. So maybe a simple way. Just wondering. So is there any other metadata that's associated with the locations? Like when we're saying, like what's the query really? Is it like show me all the places nearby to my location, or is it going to be like filtering and like some
So so in terms of filtering and all that, so I just don't think. So every place is associated with exactly one category, right? And you should provide the ability to query based on that category, right? Like optionally. So it doesn't have to be. It's not required.
Okay. All right.
Yeah. Makes sense. Yeah. Okay. Cool.
Yep. Okay. And how many query results does the like at any point, like if I'm doing a search, so I give the nearest 100 results, like something like that, or
So can you repeat that one more time?
yeah, like when I do a query, so I'm expecting the nearest 100 results, or like how many results am I expecting back? Or
okay. So you should provide the ability to paginate through.
Okay.
Yeah.
All right. Okay. So I'm just thinking. So just for the persistent storage, we can have some a data model that basically, let's see, we have a primary key, and we have a lat, a long, we have a latitude, a longitude, and we can have a category. So I can just call it a type. So let's say this is what we store, and so in this location input service, it's going to basically have an API that exposes the writes or updates for this. It'll expose a CRUD service to create and update these locations. And so for the query service, like if we simply go and query across the storage every time, so then first of all, since we are doing a query across two attributes, there's no good way to index it with the regular indexes, like a hash index or a B-tree index won't really help. But with like certain databases have geospatial indexes. So if you use like PostGIS or one of those databases that contain geospatial indexes, so then we could have the database sort of be able to query based on location. But the problem still is, even in that case, you're going to have the database be handling all of these queries. And so ideally, I suppose, like we might want to see if we can just return these results from memory. So talking about indexes and how we'll store it, so we could go like a couple of ways. So one is we could use KD trees. So this is sort of like a binary tree, but it lets you split your tree in more than one attribute. So in this case, if we do a KD tree on two attributes, we could say the first attribute is a latitude and the second attribute is longitude. So then the KD tree will help you query in log n, wherein is the number of locations you have.
Can you talk a bit about how KD trees work under the hood?
Yeah, sure. So, okay. So let's say we have this root object which contains an x and a y. So let's say this is some lat and some long. So now when you're inserting into this KD tree, so you're going to be so let's say the object the location you're inputting has a latitude that's less than this. So then it would go to the left of the tree, and locations that have a latitude that's more than this would go to the right of the tree. But now the next layer, so now in the next layer, the children now go and switch to the other attribute. So this layer is actually going based on x, and now in this layer, the children are going to be split based on y, which is the longitude. So if I have another location that needs to go, so I'm sorry, y, okay. So now if I have a location that needs to further go down, so then I'll look at the longitude. So if the longitude of this node is greater than y, so then I will go here, and otherwise, if it's less than y, I go here. So basically, at each level, I'm making a decision based on x, based on either the latitude or the longitude. So every level is going to make a decision based on latitude or longitude alternatively. And so how often do we split? So one thing is, at the leaf level, what we could do is we could determine some granularity beyond which we don't want to split. So in that case, the leaf node is basically going to just store a list of locations. So then that's the bottommost. So now when we are querying, like let's say we are given lat and long, so we keep going down, or we keep going down this tree based on, again, alternating between the lat and long. And once we, like, each of these nodes can contain some metadata as to how many locations are below it. So once we reach a node where, let's say we are looking for 50 search results. So once we reach a node that has less than that, we can include all of the results there, and then bubble up to the parent and include like some of the results from the other side of the tree as well. So that's sort of how this would work. Does that make sense?
That makes sense. Yeah.
Okay.
So how does this help? How does this help in making the queries more efficient? Like, you're going to do like a range query, where adding and subtracting, those kinds of things. Yeah.
That's correct. So, like, if you think about it, if you were just storing the locations in terms of this simple data model in a database, like in the worst case, like for example, let's for example assume that you have a given lat and long. I'll just express it as x comma y. So in the worst case, you could have like 100,000 points that are containing the same y. So now, if you wanted to find out all the points that are close to it, you would have to actually take this point and compare it with each of those 100,000 points. And so you're doing like a lot of comparisons to determine the points that are closest. But if you go via the KD tree route, so then just like in binary search, the number of locations, like you're splitting this number of locations that you're going to be doing the comparison on as you go deeper into the tree. So in the final list, let's say your granularity is 50 locations. So then you would be doing that comparison just based on those 50 locations.
Okay. I think this is good. Yeah.
So another way to represent this would also be using, so let's say we divide the world into grids. So so then like there's a system called GeoHash. So, and this is similar to a quad tree, but it's just a little more, it's like a quad tree, but instead of breaking every cell into like 4 blocks, you're breaking it into like 32 blocks. So let me draw it out here. So let's say, I'm just going to explain with 4, but the same applies in terms of 32 as well. So in this case, so let's say this is the world map, and then you split it into 4. So 1, 2, 3, and 4.
Okay.
So now, so let's say our given point lies somewhere here, right? And let's actually split this a little bit more before we try explaining. It's like this, or like this. Okay. So let's say this is our location, and this is what we want to search. So if this is our overall, if this is our world map, so then looking at it, we know that like if you compare the x and y of this point, so then you know that it's going to fall into the top right quadrant. So then you go into that quadrant, and now if you divide that quadrant also into 4, so then you can again determine which part of that quadrant it falls into. So like that, at each level you're dividing your search space by 4. So this is when you use a quad tree. And so now if you give each of these divisions a name, like for example, every time you select this quadrant, you give it a prefix A. And every time you select the top right quadrant, you give it B. And let's say this is C and this is D. So now if you can start forming strings such as, like if you form the string ABC, so then it means that the first split that you made was on the top left quadrant. And then the next split that you made, for example, let's talk about this one. So this would be something like BB. So what this really means is in the first split I made, I took the top right quadrant, so I gave it B. And then I again split and I took again the top right quadrant, so again B. So like this, I can start making strings. And so the interesting thing about this is the prefix of these strings, like the prefix of close by locations are going to have the same prefix.
Same prefix. Yeah.
So there's another circle here, for example, they both would lie in BB, even if they were in different quadrants. Like for example, let's say, like if we split up this into further, let's say these two were here. So now, like each of these will have the same BB prefix, but after this, they may have a slightly different prefix. So it could have a C or D or whatever, depending on the number of ways you split. So that would be another way to represent this. So we split up the entire world, and then for every location, we like depending on how deep we are going down this GeoHash structure, each location can be assigned a prefix. And so once you do that, so let's say we have So let's say we have a batch job or a job basically that goes and computes these prefixes. So then we can store these geohashes alongside our locations in our storage. And so now when we want to say, like, give me the closest location to like a given lat long, let's say X and Y. So we can compute, so we can compute the geohash for this lat and long. And let's say it's something like ABA, like ABCD 32 and so on. So like this, so we could start our search at this, or let's say we know that our lowest granularity is, let's say, a block of 10 by 10 square kilometers. So then maybe we are able to represent that in 7 digits in geohash. So then we could do a search in the database where we say, give me all locations with prefix ABAB2. So that gives you all of the locations within maybe 100 by 100 square. So depending on and then like if you need more results, so then like for example, let's say at the lower granularity you only get 10 results, but what you want is 100 results. So then you need to go and look one prefix higher, and then you can accumulate those results and then filter on that. So this is about how we might store this. So coming back to our service here. So okay, so our location input service is going to be basically it's going to expose some UI and some APIs to enter these locations. And once they are stored, so now we need to be able to update this index. And so let's say we go with one of these approaches. So let's say we go with the geohash approach. So then, so we probably need a service here that can compute this geohash given the lat and long. So let's say you can call it. So for every location, so this guy makes a call to the geocoding service, gets back the geohash, and then he stores it along with the thing here. And then now at the query side, okay, so you're getting back location, and so let me just write on maybe an API here. So our query is going to look like get locations and lat long and the category. And let's say, and maybe a count. Okay, so this is our input.
Yeah. So which one would you pick, the geohash or the KD tree, or both?
So let's just think of, so the geohash, there's a drawback in the geohash. The problem is like even locations that might be like very close to each other sometimes might get different, like can get different suffixes. So for example, if you're looking, if you're looking only for locations within, let's say, if your point was somewhere here, like if this was your search query, so then your query might return this object, like it might return this circle, but it might not return this circle because it lies in a different quadrant and thus has a different ending. So geohash has this drawback where nearby locations sometimes aren't seen as nearby because they have different strings.
Right. Yeah.
They have different suffixes. so one way to work like if you go with geohash, then you would have to work around that. You might have to query like the nearby quadrants as well, and then aggregate those results. But a KD tree doesn't suffer from that problem. So if you need to be accurate, then KD tree is probably makes sense to use the KD tree. Okay. So let's see what so during the input side, so we get a location that we want to store or update. So we call the geocoding service, compute the geohash, and then we either update or insert a new record into this location storage table. And so now we need to propagate these updates to the query service. So now we haven't yet computed, like we haven't done any calculations, but let's just say that in order to handle a query volume, we need more than one of these boxes. So let's say we have multiple of these query services. So now this location updates, they need to be sent to each of these. So let's say that there is an ID associated with each of them. So one thing is like ideally, I suppose a location when updated cannot like you might be updating metadata about a location, or I suppose like you could delete a place that no longer exists or something like that. But usually a given location we've stored isn't going to change. So I was just wondering if a location could change. Like for example, if these locations represented moving objects, so then I suppose we need to handle these updates. But since they are static objects, like we only need to support sort of add and delete. There isn't really an update operation. So in that case, what we could do is each of these location updates. So we can just tail the database log, and then the database log can go into a queue. So let me just make a queue here. So this is queue, and so let's say my database log, I'm just publishing it to a queue, and now each of these boxes are basically, let's say, subscribing to this queue. And what they do is when they get a message from this queue, so then basically this message contains the same structure as the record. So then using this lat long, you can drill down to since we're storing geohashes, it's basically in memory. It's just a mapping between the bottommost sort of prefix, and at each level you're associating this with a list of objects. So in essence, these query servers are basically just cache servers, and what they're caching is they're caching geohash prefixes to lists of objects, right? So if we would have some maximum bound of the number of objects that go into the lowest prefix.
Yes.
And so then when these boxes are subscribing to changes in this queue, so then those queues can just go and find the appropriate list and then update them, right? So they would either remove it or delete. So now let's say now we'll have a sort of a different problem. So let's say at the bottommost, each of these prefixes, we cap them at 1,000 locations, right? So then if you are adding a new location, then that's fine. You can just add it to the end of the list, but if you are deleting a location, so then you still, it could be in any of this. So then you need to sort of scan this list and then find that location and then mark it. So instead of actually deleting the objects and then having to move all these, you could just mark that object as deleted, and a future add can just find the first empty spot and stick the location it finds into that empty spot. But yeah, still at the worst case, I suppose you'll be checking 100 locations before you go and update the list for any particular geohash prefix. Okay, so now, so I'll actually rename this. I'll call it our location cache, and I'll actually add another box here. So the reason I separated this out is, so the query service might need to make multiple lookups as it expands the geohash prefix based on the number of results it needs. So then, yeah, so it might make one or more lookups to this location cache, and if it finds fewer results than it needs, so then it removes one character from the geohash and does another query. So with that, so once it has all these results, then it can do the comparison just among those results and give back the results to the user. Okay.
Yeah, that's good.
Okay. So now,
what kind of database is going to store the data?
Yeah. Okay. So here, so one thing is, we could use, since we don't have too many writes happening. We could use a traditional SQL database and I'm just wondering. So usually most queries will. Okay, we said we want to support worldwide queries. So yeah, if we use a SQL database, so then we can have replicas of that database, and we could shard among those databases just by let's say one way would be if we have a country, so we're sharding by country, but then again we are talking about 5 billion locations. So let's just see how much of data that is. So let's say if you look at this, so let's say this needs about 50 bytes per record, and we're talking about so 50 into, we have 50 bytes,
like 5 billion or something,
right? 5 into 10 power 9, right? Okay, so that is billion. So we have 250 billion, and so 250 billion bytes, right? And 250 billion bytes, that is basically what, 1 GB. So I suppose 250 GB, right? So in terms of storage, we don't really need we don't we could just do with a couple of database servers in terms of storing the actual locations. So let's see. So storage is not really a concern. And even if you look at the writes, so the writes, we have about 1,000 writes per second. And a typical database can definitely do 1,000, like many hundreds of writes per second. So I don't think we are bottlenecked by the number of writes either. And for the reads, for the reads, we are going to be doing, we're anyway not going to hit the database for every read, since we have this location cache that's going to be handling these reads. So maybe let's see, in terms of reads, so we said about 1 million a second. And let's say, 1 million reads a second. And let's say, since this is in memory, so let's say each lookup takes 5 milliseconds. And okay, and so if our response time is 5 milliseconds, so then so let's say we have a heavyweight server, and let's say we run 100 threads. So on that server, and so these 100 servers are 100 threads in each server is going to be handling these lookups. So let's say one server can handle 100 into 1,000 by 5. That's how many lookups. So that's like what, 200. So 200 into 100, that is 2K reads a second, right? So that is one thread. And if you have 100 threads, so we have 100 threads gives us 200K reads a second. And we want like 1 million, which is basically about 5 times, right? So it looks like, so in terms of reads, we're able to do it with like about 5 servers to handle the reads. But now, so it looks like, so since this service is global, our latency is going to be mainly determined by this where these reads are coming from. So in order to like provide these responses quickly, so maybe what we really want to do is then have these servers be have these location caches at multiple geo-distributed locations, so that the latency is minimized. But then like each of these locations again, like we'll probably need fewer servers, because even though we said we need about 5 servers to handle 1 million reads, so since these 1 million reads are going to be distributed across different locations, so we can just have a couple of servers in different locations, and based on DNS, a given query can resolve to a server that's localized to that to a nearby location. So so we talked about that. So let's see what could go wrong. So one thing is, we definitely need a replication for this location cache, and so even in each, like let's say availability zone, we might want to have redundant copies of this location cache, so that queries are still able to be served. And So let's see. And of course, we would have replication for the storage as well. But we wouldn't really need to replicate, like we can have, in order to, for disaster recovery purposes, we can have the storage also replicated into more than one physical region, but that's only to guarantee like we don't lose data. Otherwise, the queries are still going to be handled by this location query service thing. So they're just going to be replicating these updates. And,
right.
So let's see. I'm just wondering if anything else we can cover. Yeah, so we have. Okay, maybe we can just discuss a little bit about the APIs. So in our write service, we basically want to have like a store place, and then it's going to have a lat, a long, a category, and our read was anyway get places, I suppose. Why that is. Okay. So this would be a regular like post request, and like we could just use JSON and send in an object that has these attributes. In terms of the read API, we would say find places. Then we have again a lat, long, and a category and a limit. So let's maybe think about how pagination might work. So one thing is so let's say that at the lowest level, the query resolved to one of these geohashes.
Yes.
And now, and let's say you had only 10 results in that in that prefix, and so you returned all of those in the first result. And so now when he paginates for more, so now you're going to need to expand your search, right? So the one thing is, so when we are expanding the search, I suppose when you're going down to this, you already know, when you query a given geohash, you already know how many objects it has. So then if it has more than, like, let's say, and we might have a pagination, so start equal to X. So this basically is just to indicate where your pagination is going to resume from. It's basically like a cursor. So when you supply this parameter, and when you looked up this first bucket, and when you looked up the exact geohash, and let's say you found only 10 objects there, but your start is now 10. So then you know that you need to expand your search. So this guy would then expand the search and perform. So I suppose as you're paginating deeper and deeper, you're sort of having these duplicate queries that you're issuing, because you don't know that you have to expand. You don't know that you have to expand your search because you are determining that only based on the number of results in that particular geohash.
Right.
So since it's an in-memory cache, like I suppose if you limit the number of like maximum number of results he can get, so then, and if we say that each geohash represents some bounding box, so then even in the worst case, I suppose you wouldn't be making like thousands of lookups in one query. So you might do a couple of lookups, and so that might be fine repeating that work. But if you wanted to optimize it, so then I suppose you could hold on to like you do need counts at an aggregate level. Like for example, if you have this geohash, and then so you have a count here 10. So but then maybe if you start storing the counts at the parent level also, so then that gives you so maybe you like, let's just put this two things.
How does that help?
So I'm just wondering, so if I have these counts, so then I suppose it doesn't help. I was just trying to see if I can query with one lookup or exactly the lookups I need, but I don't think this really helps because even if I'm gonna let's say I want 50 results, so I'm still going to even if I start from here and then I have to look up this guy and then decide, okay, I looked up this guy and I have only 10, and so I need to do these other lookups. So I don't think it really helps.
Yeah, exactly. Yeah. Okay, cool. So I think we can go into feedback if you like.
Yeah, sure.
Yeah. Actually, sorry, let me ask you one thing. How are you doing the category-based? When I mentioned, right, like each space has a type or category. So how do you make that part also efficient? Are you going to get the results and then filter?
So so that would be one way. So these geohashes, like at the bottommost point, we said they would have lists of objects. So like if we have only a fixed number of categories, so then we could actually at each level we could have a map. So then we could have a list per category. So that would be one way. So at the bottommost level, you have a list of objects that for each category, right? So that is one way. Or if we store all the objects in the same list, so then at query time we're going to be filtering. So I suppose that depends on the number of. So if we have a small number of categories, I suppose it might make more we'll definitely be doing fewer lookups on different geohashes if we had a smaller number of if we had a list per category. So that's what I would do. So this geohash would be a mapping of type, and then it would have a list of these objects. So you would have at every level I would have like multiple. So I would have like the list of restaurants here and a list of something else here. So then during the query I look up only that particular list and retrieve these objects from there.
Cool. All right. So yeah, I think this is all great. Okay. So let's go into feedback. So I think overall, this is actually a really, really good interview. A couple of things. So I think that stood out to me, right? One is you completely drove the solution on your own, right? And I feel like a lot of candidates, a lot of students, kind of need constant input from the interviewer in order to get, input from the interviewer and ask, okay, what do I do next? What do I do next? Kind of thing. So I think for this interview, it was just like me. I was just like sitting back, relaxing, just kind of listening to what you were saying, and I didn't have to pitch in too much. So I think I really appreciate that. And that was really good. Shows that you're able to handle the kind of ambiguous problems and getting making sense of them and coming to conclusions on your own. So I think that was good. Okay, I think your breadth and you demonstrate a good breadth and depth of knowledge by coming up with different approaches to store the location index, and you explained it very, very clearly as well. Actually, I think your explanation of the KD tree was even better than what I have tried to explain in coaching sessions in the past. So I think it's very clear, very good, good diagramming, good, you know, good articulation of the request response flow. So I think all of those things was great. So I think there are, I guess, two things I would mention. So one is that I personally think that operationalization of any system is very important, right? For example, once the system's in production, what are the metrics you're going to monitor to make sure the system is healthy? Same with the alerting aspect, and how do you what are like the manual human processes involved in maintaining the system, if any, right? So that's one thing, and also and then on that note, if there are spikes in reads or writes, is there any issue in your system that's caused, right? So for example, this suddenly if there is a ton of rights to a given location, maybe Palm Springs, some kind of location that was maybe not too famous before but is famous now, right? So like, will that cause any problems to your system? Are there, like, how do you make sure your system is able to scale gracefully in that event? And also, so I think this is kind of bottlenecks, right? Yeah. And lastly, I think I don't think we talked about sharding of the database, did we?
No, I didn't really touch too much about
Yeah,
that.
exactly. Yeah. So I feel like so I feel like the sharding was one of the bigger things I think we should have talked about. I think I just realized that we didn't talk about it. Actually, let me quickly ask you then, like what are the sharding options, and which one would you pick? Yeah.
So in this case, like one thing is by country, like that seems like the natural sort of like any given query is going to be hitting a separate.
Okay.
So, but then like a country, like we said, we had like about how many billion? 5 billion locations, right? So
yeah.
So sharding by country seems all right. Like I think even if you divide by 10, like you get less than 1 billion, like 500 million locations per thing, and that's not something a database like it will struggle to handle. So let's see. Or the other way, I suppose, is so I suppose, yeah, like again, this country, going by country is sort of tricky because now the query that might start following the time zone. And so like your peak queries might be in certain locations always at certain times. So maybe you could shard by like the geohash prefix, like you could shard by that. So then at least you know that nearby queries are going to hit like for example, if you shard on the geohash, like on a prefix of the geohash, so then like your lowest location will still sort of be always hitting one shard, but in a given region, you're still distributing that among the queries will still get distributed among multiple shards. So that that might relieve, but it depends on how granular your lowest location is. Like if your lowest location itself has a very popular place and everybody's going to query for that, so then that's a problem. But I suppose that is still something that can be solved by replication. So if you have like if you still if you have enough replicas, then you still would be able to handle that query load, but distributing among them. Yeah, that's what I'm thinking.
Cool.
Yeah, I would think sharding by a prefix of the geohash might be the best way to go here.
Yeah.
If you start by ID, then you're going to do like scattergather and yeah.
Yeah, I mean, I feel like there are pros and cons here, and I think it probably, I think you laid them out pretty well. I feel like the sharding decision depends on the distribution of the locations around the planet. For example, if there are too many locations in a given geohash, for example, San Francisco, New York City, or something, then I think sharding by it will require maybe even further vertical sharding, right? So I feel like that might be one issue that I see, right? So that's one issue I see. But then, otherwise, but then of course the con of that is scattergather, as you mentioned. Yeah. So I feel like that. I think just to recap, So I think the sharding, I think you answered it well, and so I won't put that in the feedback. It's okay. So I think again the main things I would say are, I think you pass the interview, I feel, but the main things are maybe the operationalization, how do you deal with spikes and reads and writes, and any human costs associated with the system. That's more like a operationalization thing. For example, if you went with the geohash based sharding, you may and suddenly there's a write and read traffic to a particular shard, and that shard cannot handle it, then the on-call might get pulled at 2 a.m. to add more shards to that system, right? And it's never as simple as auto scaling, right? This is a stateful, like database server, will require bootstrapping, and maybe it may require getting additional hardware from somewhere, right? Anyway, that's just a random thought, but that's one thing that I see. Yeah. Cool. So I do have a meeting now, but it was nice talking to you, and I will give you written feedback. Any last minute questions I can help with?
No, I didn't have any.
Sounds good. All right, cool. So that should be it. Thanks for taking the time. Yeah.
Cool. Thanks. Yep. Bye-bye.
Take care. Bye.